Welcome back, students. In this video, we are going to talk about what is called as transformers. No, these transformers are not toys that you know. These transformers are instruments which help you convert one AC voltage into another AC voltage. I will be able to take an AC voltage of say 100 volts and convert it into 150 volts or 200 volts or even just 50 volts. So I can do this using a transformer. So doing so helps you transmit power over long distances with minimal energy loss. So the efficiency of transmission is improved. How? That is something we'll discuss a little later. But first, I want to talk to you about the instrument called as the transformer. A transformer works on the principle of electromagnetic induction. It has two coils. One is called as a primary coil and the other one is called as a secondary coil. There are many different ways you can put these two coils together, but I start with one simple way of putting these coils together and then see what happens. So I've taken two coils. Okay, this is the first coil. Okay. This is coil 1, or in transformers they call it as a winding one. Okay, but let's call it as coil 1. Suppose I apply a voltage, an AC voltage across it. So this is V. It's equal to Vn sine omega t. Then this is going to set up a current in this. And there will be a voltage, a back EMF that is getting created from this, where this current is changing. So as a current, this current will produce a flux, and that flux is changing because the current is changing, and because the flux through this coil is changing, there is self-inductance, and because of the self-inductance, then you have back EMF that will oppose this. So this voltage V, I'll call this as Vp, it's better. So it's VMP, sine omega t. Vp is, this coil is called as Cp now. So P stands for primary. This is a primary coil. So there is an EMF induced and that will oppose this. So this EMF, this voltage and then that EMF will be equal. And then there will also be a current circulating through that. Okay. Okay. So what will this do basically? So this current will set up a flux. Yeah. So how can I express this? So Vp is equal to minus N d phi by dt. I hope you agree. So this is actually equal to the back EMF, first of all. This is actually equal to the back EMF that gets generated here. I'll call this as E. And if there is an ideal inductor, there is no resistance in this inductor, then this will also be equal to Vp. Because Kirchhoff's law has to be obeyed. There is no resistance across which there is a voltage drop. So all the voltage that you apply should be applicable here, and that must match the back EMF. So Vp is equal to minus d phi b by dt. So what is this phi b? Phi b is set up by this current. Yeah, this current will set up a phi b. And what is this N? N is the flux linkage. So because this current is changing in every loop, there is an EMF induced. So there are N loops. I'll call this as NP to be precise. Okay. So this voltage must balance this voltage. This you know. So this will set up a field. Maybe something like this. Something like this. Okay. So the field will be here, everywhere. Okay. But then as you go further away from this, then the field strength will be small. Anyway, what I'm going to do now is that I'm going to bring another coil. This I'm going to call as secondary. Maybe more number of terms. So let's say this is open. So this is called as the secondary coil. Okay. So what is going to happen now? Because this current is changing, the flux will be changing, and then part of that flux goes through this coil, and I'll call that as maybe this is phi B is total flux, and this I'll call as say phi ES. Okay, this is different from phi B because you see phi B is everything, but there is only a fraction of that coil that goes here, and that links this coil. And because this is changing, and that will also be changing, and there will be EMF induced. Okay. So what's the EMF induced in this? The EMF induced. Okay. This is I'll call this as P, and the EMF induced ES. Okay. Is equal to minus NS. Now it's number of turns in the secondary, and D phi S by dt. Okay. Look at this. It's like different. These two are different things. This is phi B, the primary, the entire, all the flux here, but only a part of the flux is going there. So you get this. Okay, but this will be related to this in some way. Correct? Because if this is going to increase, this will also increase. Flux through this will also increase if the flux through the primary coil increases. So there is some kind of a relationship. Suppose I give a path for all the flux to go through this. If I can somehow make all the flux which is produced by this to go through this, then what is going to happen? And this flux linkage is more. Like whatever flux is here will be here too. So I can maximize this. I will not be losing this flux. This flux is also changing, but I will not make use of it here. But if all the flux is going to go through that, then what? All the change can be effectively used here. So to effectively use this, I am going to have what is called as a core. It's a soft iron core. So if I put a soft iron here, and if I wind, this coil around the soft iron, then you see I have a coil like this, I have a core like that, and I'm going to wind the coil around this. Then what is going to happen? Two things will happen. This kind of provides a path for the flux to go through. One. Second, because I have soft iron core, the field will be increased. Because like if you have an infinite solenoid, then what is the field strength? That is B is equal to, for infinite solenoid, B is equal to mu naught Ni if there is no core. But if we keep a core, then the same B becomes mu or mu naught Ni. So you see now, if this is say 1000 times, 1000, if mu r is 1000, then the same B for the same current, the magnetic field for the same current is increased 1000 volts. So this does two things. One, by having a core, I provide a path for the flux to flow. All the flux will flow through that. And second, I am increasing the magnetic flux through the coil. If this was not there, the flux through this coil was something like this. Not exactly, because it's not an infinite solenoid, remember. But it will be something similar, right? Mu naught Ni. But now I have provided this, so it's going to be mu r mu naught Ni. So I have also increased the field, the magnetic field strength. Okay, so this is coming like that. Now what I'm going to do, I'm going to extend it so that this follows this magnetic, and then I'm going to wind the second coil around this. Now you see there will be very small leakage. Almost all the flux will now, almost all of it will go through. So almost all of it, all the flux here will go like that. Almost all flux will go like that. There will be very little which will be outside. Almost all of it will go through like that. So I provided a path for it. So whatever flux which links here, almost all of it will be available here. So this becomes, this part becomes approximately equal to, okay. So there is an EMF induced in this too. Okay. So this is plus minus, and this will be plus minus induction, and here also this will be plus minus. So this is a voltage, this is secondary, and this is primary. And if there is no current flowing, then even the terminal voltage you can take it as Vs. Whereas Vs is equal to induced EMF. So that is what I'll get. So this is also equal to Vs. Okay. So I give Vp here, and that Vp is equal to EP, assuming that it is all perfect in the ideal condition, and there is no resistance. This is what we are going to have, and if I keep this as open, or very little current is drawn from this, then this ES will be available here because there is no voltage drop on the wires. I hope this is. So what have we got here? I'm going to use these two equations now. This is one, and this is the second one. So Vp is equal to minus Np d phi b by dt, and Vs is equal to minus Ns d phi b by dt, because we provided this for almost all of the flux to go through. There will be very little flux leakage if we provide a core like that. So the purpose of the core is that basically you are providing a path for the flux to go through. Okay, so now, so this is my first equation, the second equation. Look at this. Then what's the ratio? Look at the ratio. So Vp by Vs is equal to Np by Ns d phi by dt will cancel. So this is an amazing result. Why is this an amazing result? Because I can have any voltage here, and that voltage can be converted into this voltage depending on the number of turns here. If you adjust the turns Np and Ns, then I can get any voltage I want here. I can start with say 1 voltage, I can probably get say 1 million voltage on the other side. That's very easy. You don't need anything else except the turns, the number of turns. You have say 10 turns here and then 10 million turns here, then ideally you must be getting, if I apply 1 volt here, then I must be getting 1 million volt there, yeah, because of this ratio. So for example, if the primary is Np, value is say 100 turns, and then if the number of turns here is equal to 1000, then clearly Vp by Vs here is going to be 100 by 1000 into 1 by 10. So what's Vs? So this gives you Vs is equal to, goes there, comes there, then Vs is equal to 10 Vp. So whatever voltage I give here, it will become tenfold on the other side. So now the output voltage is in my control. I can get any voltage I want, provided given any voltage, I can convert that voltage into any. You give me 1 volt, I can convert it into 1 million volt theoretically. Or you give me 10 volts, I can convert it into say 1000 volts or 2000 volts. Or you give me 1000 volts, I can convert them into just 2 volts. That's also possible. That is, I would be changing this. In this case, I have 100 and 1000. Suppose if I had 1000 turns for the primary and just 100 turns for the secondary, now my secondary voltage will be 1/10 of Vp, not 10 times Vp, 1/10. So if I get 1000 volts, and if I use this term, okay, 1000 for this and 100 for this, then I will get just 100 volts. 1000 volts input, 10 volts, sorry 100 volts output. Or I can give 1000 volt input, and if it reverse the number of turns, then I will get 10,000 volts. It's like this. I have a transformer now. I have power supply. If I connect it to, suppose this has 100 turns. Suppose we get 1000 turns. This one has 1000. I take the supply, I connect it to this coil. Then what's the voltage in the coil? It should be 10 times more. Suppose this is 100 volts. Then this would become 1000 volts. I take the same thing. I connect it here. So then the input is going to be equal to 100 volts now. I have taken this, connected it here, and I am keeping it open. Then what would be the output here? So this will send a current, and that will produce a flux, and that will change. This will now, get an induced EMF here. And now how much would that be? If you have 100, and this will be just 10. So it depends on where I am going to give the input. Am I going to give the input to the coil with more number of turns, or to the coil with less number of turns? Okay? If I give the input to the coil with more number of turns, then my output will be less than the input voltage. If I give the input to the coil with less number of turns, then my output voltage will be greater than my input voltage. And just by adjusting the number of turns I have in each coil, then I can give any input voltage and get any other output voltage I want. It's totally in my control. Okay? So this is the fundamental principle of a transformer. because it transforms the voltage. Okay, this is actually this transformers transform they transform the input voltage into a different voltage. So that's why you call these things as transformers. So this is the basic principle of it. Okay. Well, how can you get this first of all? How can I convert just 1 volt into a million volt? Or a million volt into just 1 volt? How can I get this without something else happening? Okay? If I gain something, then I must lose something. Nothing is free in this world, right? So if I gain the voltage, then I must lose something else. What is that something else? Okay. What do we know? One of the basic principles of nature is the law of conservation of energy. And obviously, when you talk about energy, you also talk about power. Okay? So, there must be this law which is obeyed. The law of conservation of energy and thereby power. Okay? If you're using energy at in both places at the same rate, then power also should come into play. We're backing on the law of conservation of energy. Okay. Now, what is the power here? Okay, let's say I've had this circuit and Vp is input voltage and let's say Ip is the current through this circuit. Let's say this is Vs and now I'm going to connect another resistor here or a load resistance. Okay. I'm going to connect this load resistance. Now there is a current which is going to flow through this, so this is Is. So the current through the secondary, this is a primary coil, this is called the primary coil, told you, and this is the secondary, right? Okay, this is the secondary. So the current through this is Is, the current through this is Ip. So Vp Ip must be equal to Vs Is. Okay? So whatever energy you give must come out there. So the law of conservation of energy must be obeyed. So what does it give you then? So Vp Ip must be equal to Vs Is, and this happens at every instant. Yeah. So Vs Is. Vp Ip, the energy that should be here must be equal to Vs Is. The energy that you take out the power here, but you can relate it to energy. Okay. So Vp Ip is equal to Vs Is. Now, what is my Ip by Is? Ip by Is is equal to Vs by Vp, and that must be equal to what is Vs by Vp? Vp by Vs is Np by Ns, so Vs by Vp must be Ns by Np. Okay, so this is Ip by Is is equal to Ns by Np. You see here? So Vp by Vs is Np by Ns, but Ip by Is is Ns by Np. This relationship is getting inverted here. As you get a reciprocal of this relationship when you compare the current in this with the current in that. voltage in this divided by the voltage in that is Np minus divided by Ns. But current in this divided by the current in that is Ns divided by Np. Okay? So what does this tell you basically? What it tells you is that I can convert this voltage into a bigger voltage here by certain factor. But take this. Then this current will also be converted into Is, but then that will be less than this current. If this is more than that, voltage is more, Vs is more than Vp, then Is will be less than Ip. So this is where things get balanced. So I take 10 volts. I take a simple case. Okay, I have this primary. Okay, this is primary. So I have Vp applied across this, and then Ip is going through that. Let's say Vp is 100 volts, and then let's say Ip, say 10 amperes, like that. And here I have another coil, secondary. This is secondary, right? In the case secondary coil, let us suppose that I get 1000 volts. That Vs is equal to 1000 volts. And then the current Is must be equal to 1 amp. Why? VPIP must be equal to VSIS. You cannot violate the law of conservation of energy. So VPIP must be equal to VSIS here. If this is 100, this is 10, then VPIP is 1000. If this is 1000, then this has to be 1. Okay? So in an ideal case, thinking that all the energy that you give here is available here, then this works. So you can see that if you gain on the voltage, you lose on the current. If it's the other way around, if it is 1000, then it becomes 100, then you have 1 ampere, and then that will become 10 amps here. If the input is, if you take this as a primary, this is a secondary, whatever, okay, then that relationship will exist. Okay, so this is a fundamental principle. What have we done here? We have transformed the voltage and of course the current. There is an input voltage and that is getting changed to some other voltage using this arrangement. You have a core around which you have two coils, the primary coil and the secondary coil, and you give the input to the primary coil and you take the output from the secondary coil. Okay, so the voltage is getting transformed that way. But in both cases, the energy that you give, the ideal condition, is not wasted anywhere else, then must be available here. So to produce this voltage, you need to give energy. Then if the voltage is produced, then you know that the current is circulating, and clearly this energy must be same as this energy. So that is it. Then you get this. Okay. Now there are two types of transformers. Step up transformer and then step down transformer. Okay. What's a step up transformer? Step up. So the output voltage is more than the input voltage. You have 100 volts, it's 1000 volts. So you're stepping up. So voltage, not current, keep in mind. Voltage, step up voltage. Okay, you are stepping up the voltage now. It's 100 volts, with 1000 volts output. For 100 volts input, if you get 1000 volts, or 2000 volts, 4000 volts, or even 150 volts, if the output is greater than the input, then it is called a step up transformer. Step down is the other way around. If the output is less than the input voltage, then you call it a step down transformer. In this case, you are talking only about the voltage, not about the current. The step up transformer, the output voltage is greater than the input voltage. The step down transformer, the output voltage is less than the input voltage. For example, what you see near your house as a transformer, the ones that the TNEB, Tamil Nadu Electricity Board, that installs huge transformers, very huge transformers. They are step down transformers basically. Okay, because I'll tell you like why it is done that way. I'll tell you shortly what is the use of all this. Why is it beneficial to you? Okay, but what you see out there near your house is a huge transformer, it's a big transformer. But then I have a very small transformer, the size of my, it is like it's less than the size of my thumb. Okay, this is also a transformer. I don't know if you can see it clearly, but there are two windings here. Okay, but now what I've got is this is a different kind of winding. Here I wound it like this. But in this case, in this transformer, which I've taken from a back mobile charger. Okay, so your mobile charger will have transformers like this. The modern ones are really small. But if you just go a few years back, then the transformers are a little bigger than this. But modern ones are like, they've perfected the art of making this, and so they're very small. Okay, so they're so small, it's a transformer. It's there in your mobile charger. Anyway, so, but this winding is slightly different. It's like this. So you have a core. Okay, I'll use the same color. So use there. So this is the core. Okay, and then what you do is, if you're going to say the primary, you're winding the primary around it. I'll tell you this. Okay, this is the primary, you wound the primary around it, so it's going to produce a flex or something. Then what you do is that you're also going to wind the secondary around it. Okay, so you'll probably get this and this, or if you want, you can take it out down the other side to be more clear. I'll say this is this, and maybe it's like that. So the primary and secondary are wound on the same leg. Okay, so this becomes your core. This is the core. Anyway, like now this is more efficient because you see, almost all the flex produced by one is going through the other two, right? So this is a much better design than this, and that is what you get here. Okay, there is a single, there is a core, there's a core here, and then the wires are wound around that core. Okay. It's a very small transformer here. Okay. How does this function basically? And this is your another charger. I bet you'll be seeing a transformer inside this. What does it do basically? What is the typical voltage you require? Okay. What is the typical voltage you require to charge your mobile? 5 volts. But what is the voltage which is coming in your power socket? 220 to 240 volts or something. I cannot directly give it. Then what should I do? I should step it down. So in this transformer, the transformer you have here, the prime number of windings, the number of turns in the primary will be more than the number of turns in the secondary. because you are going to take 220 volts or 230, 240 volts input, and you are going to convert that into maybe a 5-6 volt output. So the secondary will have less number of terms in this ratio. Okay, and you will also have a rectifier circuit, because you get the output at 5 volts, but you also need a DC for your mobile. So this will have both. This adapter will have a transformer to step down the voltage from 220 to maybe 5 volts, okay, 5 volts, and it will also have a rectifier circuit, which you studied in your semiconductor lesson, to convert that AC into DC, and that is what is available here. So you will have diodes and a capacitor, a filter. So that kind of an arrangement will be here inside. So it has two sets. A part is from this lesson, and the other part is from your semiconductor lesson. You can either have diodes, or sometimes they use some chips, okay, which do the same function as the filter or the rectifier circuits, okay, do that. So same thing happens there too. Okay, so this is what you have here is a step down transformer, because the output is less than the input. I want you to keep that in mind. Okay, now let's see how a transformer can be used profitably for us. Let me take this as your house. You have an electrical connection here, right? Okay, you have, let's say this is your load. You have all your appliances here, your fridge, your TV, your electric heater, mixie, grinder, everything. Okay, this is your load. Okay, and now this has to be supplied by whom? By the metro power station. So effectively, the power you receive at home has to come from metro. So this is your metro power station. Let us suppose they are doing it with DC voltage. Okay. And from metro to your house, the distance is approximately 60 kilometers. It's too long. kilometers. And let's assume that the wires they use are nearly perfect. It's very good quality wires, and you have only 1 ohm of resistance per kilometer. So for 1 kilometer length, you have only 1 ohm. It doesn't happen. But let's assume that is what you have. So for the 60 kilometer distance from the power station to your home, then you will have 60 ohms of resistance in one wire. This will be 60 ohms. Assuming that you have 1 ohm per kilometer, this is an ideal condition basically. Okay, this doesn't happen. This doesn't happen actually. It's like 1 ohm per kilometer. Okay. So, and this is one way, and there is written pathway for the current to go. So here also you will have 60 volts. Okay. Let us suppose that your load, your resistance, the net resistance at your home, okay, that is say 100 ohms. This is your resistance, this is RL. So 60, 100, 120 ohms, 220 ohms. Let us suppose this voltage supply is also 220 volts. So clearly, that is the current of 1 amp, I is equal to 1 amp flowing through the circuit. So 220 volts divided by 220 ohms will give you 1 amp current. Okay. But let us see what is the voltage available here. This is 60 volts will drop here. Then 60 volts will drop here, because 1 into 60, 1 into 60, then 120 is gone, and the voltage that is available for you is only 100 volts. Okay? Now, the voltage they generate is 220 and the voltage you receive is only 100 if you are directly transmitting using a long wire. And this becomes even worse when you consider some other place like Coimbatore. That is another 60 to 80 kilometers from here. Okay? So instead of you being at Gobi, let us suppose that you are at Coimbatore. So which means roughly another 60 kilometers. Actually 80, but let's say 60. So then we will get 60 ohms. 60 ohms is the best case scenario. And then you have 100. Let's see what happens now. So you have 120, 120, 240 plus 100, that is 340 ohms in the circuit. There are 220 volts. So what's the current here? The current changes to, now the current changes to 220 by 340, that is 11 by 17 amperes. Previously it was 1 ampere, now it is 11 by 17, much less than 1 ampere. So that's the current which is going through it. What's the voltage you are going to get? Well, this is 120, that is 240. So the current, the voltage drop across these resistors will be, 11 by 17 into 240. Okay, and this would be how much? Or I can even take this and then multiply it here, right? So the voltage across this would be simply 11 by 17 into 100. So 1100 by 17. So if you do that, almost, if you take it as the 20, okay, then 110 by 2, 55, it's approximately 55, maybe like you're getting 60 volts or something here, okay. So 60 to 70 volts is what you get, maybe somewhere around 60 to 70 volts is what you get here. That was in Coimbatore. If your house was in Gobi, then you were getting 100 volts here. And if your house is in Coimbatore, then you are getting about 60 to 70 volts. You see, it's coming down. So the current you can draw is also coming down. So the power you can draw, V into I, is coming down for you. So you can draw only less power from there. If your house is in Gobi, you will draw one amount of power. And if your house is in Coimbatore, you will draw a different amount of power for the same appliances. Because this distance adds resistance to transmission, and that affects your voltage and current draw. And it's not only that. Then what happens here is that as the distance increases, there will be a lot of power loss here. Okay, lot of power will be lost. Okay, like let's suppose that I take this case. 1. You are at Gobi. So this is your resistance. 60, 60, and this is 100. Okay, and I am also in Gobi, so I have another. I will contribute another 100 to it. Okay. Now let us see what is happening. So this is 220 volts. Previously 1 ampere was flowing, right, for this setup. Now I too have taken the connection. If once I have taken this connection, then you see this net resistance from this would reduce to about 50. So 60, 60, 50. So 120, 170 is the resistance here. Okay. So you get the current now is I is equal to 220 by 170. So this would be more than 1 ampere. So this is going to be more than 1 ampere. What is happening here then? What is the power loss here in the line I squared R? So 1 squared into 120. So 120 watts was being lost here. But now you see you have more than 1. And the power lost in transmission is more than this 120. So somebody else has taken the connection. So now you are supplying to this guy and you are supplying to the other guy. Then the current through the line is increased. As the current through the line is increased, the I squared or loss along the line is also increasing. So the power that we generate here, more power is lost along the wires, along the transmission lines. So less power will be available for them. So there are two disadvantages in this when you use DC. Okay? One is, as you go further and further and further, then you have this issue of the voltage getting dropped. And when you supply more and more current to your subscribers, then there will be more and more loss in the circuit, much more loss in the circuit. So you will be wasting a lot of energy in transmission itself, and by the time that guy gets it, will be much less. As you saw, 220 volts, you get only 100 volts here. Okay, and then here only you get about 60 to 70 volts, and if it is much farther, much less. So the instrument also will not work well. So these are the disadvantages of long distance power transmission. But what will happen when you use a transformer, or when you use transformers? What I'm going to do is that instead of DC, I'm going to have AC. Okay, in AC, I'll have AC power source here, and then I'll have a transformer. Okay, so this is 220 volts, and then I may have a step up transformer. So I'm going to transmit power at a much higher voltage. Maybe this would be I'm going to have a ratio of 1:1000. Okay, so which means 220 kV or 220,000 volts. That is the voltage available here. So I supply 220 volts here, I get 220,000 volts here. Okay, so now I transmit. Now I have the same 60 ohms here, and I have the same 60 ohms here. Then this is Gobi. At Gobi, I'm going to step it down, because I can't use this high voltage at home, because there will be lots of accidents. So then from here, I'm going to step it down to say 220 volts. Okay, so this is what it is. Okay, there is a step down transformer which will have this 1000:1 ratio. Okay, 1000:1 ratio. You have 1:1000 ratio to step up. There you have 1000:1 ratio to step down this voltage. There will be a certain voltage which will drop here. We'll see like how much it's going to be. But let's understand this. So you're stepping it up with 1:1000. You're stepping it down with 1000:1. Suppose I connect a load here. Alright, let's see what is going to happen. So suppose this load requires 1 ampere of current. So 1 ampere of current is flowing through it, let us suppose. If this is 1 ampere of current, then how much ampere of current will this line draw? This line will draw 1,000th of it, right? Because 1000:1, you know that ratio. So if the current has to, this has to become, the voltage is less, Vp It must be equal to Vs Is. So the voltage is less, then the current has to be more. So if 1 ampere is a current, then this would be just 1 milliamperes. So 1 milliampere flows through this circuit. What would be the voltage drop across the resistor? So this will be 120 ohms into 1 milliampere. So you will get 0.12 volt drop. Okay, so only 0.12 volt, 120 by 1000. into 10 power minus 3 volt. Okay. So you get 0.12 volt. You see, you have 220 volts, then using 1:1000, you get 220,000 volts, and out of which only 0.12 volt will drop. Meaning, all this voltage, almost all this voltage will be available here. And if all this voltage is available here, what would be here? Roughly the same 220 will be here. Almost this voltage will be available here. You see, in one stroke, you have changed two things. One, the applied voltage is the same for your appliances. So you can use this appliance here, or you can use your appliance in Coimbatore. In Coimbatore, what would have happened? Same thing. So now you have, instead of 60, then you will have 0.12, you will have 0.24 volts or something. And how much difference is it going to make to this? Much less, right? 220,000 volts minus 0.2 volts, or 220,000 volts minus 0.24 volts. Hardly makes any difference. So this voltage which is here will be almost the same here, and this will be almost the same as this. So you have predictability. If I generate electricity at 220 volts, I can expect it to be at roughly 220 volts here. Okay, and the power loss, you see, is much less. I have only 1 milliampere. Previously it was 1 ampere was flowing through it. Now it's only 1 milliampere is flowing through it. So I squared R, I would have reduced it. I would have reduced the power loss by 1 million. The power loss here is only 1 millionth of what the power loss was happening here. Okay? If 1 million watts was dissipated here, I am dissipating only 1 watt. You see what a drastic change here. So by using transformers, I can have these two advantages. I cannot use transformers with DC because the flux has to change. DC doesn't do that. It's a constant voltage. So transformers cannot be used with DC. They can be used only with AC. And that is the reason all long distance power transmission takes place as AC. And this is the reason you have AC voltage at home. If DC is to be given to your houses, then there will be a lot of power loss and voltage drop as you transmit for long distances. But if AC is used, you can get almost the same voltage as the voltage at which it is produced. Okay, whatever rating that your instruments have, I can maintain that voltage using transformers because I can control the power loss in transmission by appropriately stepping it up. If it steps up, then the current it draws will be proportionately reduced here using this step down transformer. So the current can be changed. So the current can be changed, then the power loss will be less, and also the voltage drop would not be much. So clearly, almost all of this voltage can be available there. So for these reasons, AC is used, and this is the reason why you don't get DC at homes, but AC. Hope this is clear to you.